Welcome to Unit 1, Lesson 6, Multiplying and Dividing Rational Expressions. In this lesson, we're really going to use all of the same skills that we learned in our previous one. We're going to just add the additional fact that sometimes these rational expressions are going to be multiplied together or divided by one another. But the nice thing about dividing in this case is that it's really like dividing fractions. And if you remember, dividing fractions was actually almost as simple as multiplying fractions in that any division statement can be always thought of as multiplying by a reciprocal. So in order to tackle these, what we're going to do first is always express each of them as a product. So even if we see some of them written as division statements, we're going to use the fact that division is really just multiplying by the reciprocal in order to express each of these as a product. And then we'll do the other three steps just like we did in our previous lesson. Factor the numerators and denominators. Use those to help us state any restrictions, and even more importantly, use those to reduce it as much as we possibly can from there. So let's just go through some examples and see how this works. So right now we've got these first two pieces here that are just multiplied together, and then they're being divided by this third piece after. So the first two pieces are already essentially forming what will be a product. We'll really just need to multiply their tops and multiply their bottoms. But we need to do a bit of work with that division piece as well. So let's rewrite this as a total product statement. So I have 12x cubed over 7y to the fourth times 14y squared over 8x squared. And now I'm going to say it's times 1 over 2x squared. So I'm multiplying by the reciprocal to make this into a multiplication statement. A full product, essentially, is what I'm looking at here. And now, let's look at any places we can reduce. Well, if I look at my first factor here, or my first piece, I have a 12 on top and a 7 on the bottom, but those aren't the only places that I can look, because remember, everything on top is going to be multiplied together into one big giant term. Everything on the bottom will be multiplied together into one big giant term. So let's look at any factors on top and see if they can reduce with any factors on the bottom. So for example, this 12 here can be divided by 4 to leave a 3. And I'm allowed to do that as long as I find some factor on the bottom that I can also divide by 4. So how about I divide 8 by 4 and leave a 2? Let's do it with some other things. What about, I have a 14 here that can be divided by 7. That's going to leave a 2, as long as I find that I can divide this by 7 as well and leave a 1. Is there anything else I can do? Actually, I can go one step further, because I actually still have a 2 here that I can now reduce even further to just a 1, as long as I divide this by 2 as well to leave a 1 here. So let's put this all together now and see what we've got, because that was a lot with the numbers. So let's just work on thinking about what our numbers are going to be. So on top we have 3 times 1 times 1 in terms of the coefficients. So our coefficient is just going to be 3. And then we have x to the power of 3 and y squared. On the bottom, it's 1 times 2 times 1, so our coefficient is 2. And I'll write the x's first in this case. It would be x to the power of 4 and y to the power of 4 as well. And now I need to reduce my exponents on my variables as well. So I've got 3 powers of x on top and 4 powers of x on the bottom. So that means I'm going to have 1 leftover power of x on the bottom. So I'll have a 3 on top still and a 2 on the bottom, but I'm going to have 1 extra power of x left on the bottom and no powers of x left on top. Then I've got 2 powers of y on top and 4 on the bottom. So that's going to leave, well, no powers of y on top and 2 powers of y on the bottom when I reduce. But now I need to go back and say, what can my variables not be equal to? Well, definitely if x was 0, then this wouldn't work. but it's also true that y can't be 0 either. So because we have two different variables here, we have restrictions that actually are involving both of our different variables. So neither x nor y could equal 0. Once again now, we have a division statement. So my first step is going to be to rewrite this by multiplying by the reciprocal. And along the way, I'm also going to just take into account the fact that there's really only one negative in this entire thing, and it happens to be on the bottom here. What that's really going to do is just make this overall entire expression negative, because it's really like we're taking a positive rational expression and dividing it by a negative rational expression. And we know when we divide a positive by a negative, it makes our entire thing negative. So in my next step, rather than thinking of the negative on the top or bottom of that second rational expression, I'm just going to put the negative in front of the entire thing. And so we could actually write the negative on top of the fraction, or we can write the negative in front of the entire fraction. We just never leave a negative in the denominator. The rest of it, though, is going to be 63 a cubed c squared over 45 ab squared that I already had. And then it's going to be multiplied by, I'll put the 15 ab cubed c on top, and 36a squared b times c to the fourth. And now I try and reduce as much as possible. So let's reduce the number parts first. Well, if I want to, let's say, divide this 63 by 9, I can actually do that. So if I divide that by 9, it leaves me with 7. And I can do that as long as I divide something else by 9 as well. Well, how about I divide this by 9 and leave a 4? I can do something else, though. I can also divide this by 15 to leave a 1, as long as I divide this by 15 to leave a 3. So just in terms of the numbers involved in my next step, I would have 7 times 1, or actually I should put that negative in front of the whole thing first. I have 7 times 1, and then in terms of my a variable on top so far, I've got a cubed times another a, so I'm going to have a to the power of 4 on top, b to the power of 3, and with my c's I have c squared times another c, so I have c cubed on top. On the bottom, I have coefficients of 3 and 4, so when they multiply, it's going to be an overall coefficient of 12. And then I have 3 powers of a, I have 3 powers of b, and I have 4 powers of c as well. And now I need to reduce my variables using exponent laws. Well, I'm going to still have negative 7 over 12, but in terms of a's, I'm going to have 1 leftover power of a on top. The b's are actually going to completely reduce one another, so it's kind of like I'm dividing both the top and the bottom by b cubed, and they just become 1s, and they won't need to be written anymore. And then for c, I can eliminate 3 of my powers on top and 3 of my powers on the bottom, but that's going to leave still 1 single power of c on the bottom of this expression. So negative 7a over 12c is the simplest way that I can write this. But again, notice that if any of those variables had been equal to 0, the entire denominator would end up being 0. So that means a cannot equal 0, b cannot equal 0, and c cannot equal 0. None of those things can be true, and as long as none of them are true, this still represents a rational expression in its simplified form. Now let's see how some factoring skills can help us out in some of our later examples. So now for question C here, one of the things I'm going to do in my first step, of course, is change this division to a multiplication, and I'll do that by flipping around this second fraction. But another thing that I want you to keep in mind and take a look at is that I'm going to be trying to look for common ways to reduce. And right now, every expression except for this one has the thing with the higher exponent first. So right now we have the term that has the lower exponent, the 6x, coming before the higher exponent, the negative 3x squared. But everything else has the opposite order. So I want to do that trick again where I flip around the order of that little expression there. Well, I can do that by factoring out an extra negative sign. Or even just for now, just to make it a bit simpler, I think a bit more straightforward, why don't we just flip the order of those? So I'm going to put the negative 3x squared first and the plus 6x second. And I still have 4x plus 20. But then I'm going to multiply that by, well, I'm going to put 3x plus 15 on top now to make this the reciprocal. And 9x squared minus 18x goes on the bottom. And now I'm going to start factoring. So on top, in this first expression, I've got some common factoring I can do. I can common factor out negative 3x. That's going to leave an x minus 2. On the bottom of that one, I can factor out a 4. That's going to leave x plus 5. For the top of the next expression, I can factor out a 3, and that's going to leave an x plus 5 as well. So that's handy to keep in mind for later. And on the bottom of this one, I can factor out a 9 and an x, and that's going to leave an x minus 2, which is handy to remember for later as well. So let's start to do some reducing now. First off, just before I even look at the factors, let's just think about the numbers involved. So this negative 3, how about I divide it by 3 to make it a negative 1? And I'll divide this 9 by 3 to make it a 3. Well, I can also divide this x by x to leave a 1 and divide this x by x to leave a 1. I can keep going. I can divide this x minus 2 by that exact bracket to leave a 1, and I'll divide the bottom by x minus 2 to leave a 1 there as well. And hey, I can keep going even further, running out of colors here. X plus 5 can be divided on top as long as I divide the bottom by x plus 5 as well. So there are more common factors that can be reduced on the top and bottom. So that was a whole lot of simplifying. What do I actually have left after all of that? Well, on top, I have negative 1 times 1 times 1 times 3 times 1. So really, I just have essentially like negative 3. And on the bottom, I would have 4 times 3 is 12. And actually, this sometimes happens. You might do a whole bunch of reducing and realize you actually could have reduced it even further. And so here's an example where I realize I actually missed one of the reductions that I could have done in terms of my numbers. And so I can reduce this even further. And it's actually just negative 1/4 because both the top and the bottom can be divided further by 3 in this case. So that's what's nice. Even if you miss one of those reductions in your big reducing step, like I did with all my colors there, you'll still be able to catch it later on. You're not necessarily going to have to do it all in one single step. And so that's okay if you notice later on that you can actually reduce it even further. And as many steps as it takes is totally okay. So with all that being said, we still need to go back to our original factored form and think about all of the different things that x could not equal. Well, that factored form tells us that x could not equal 0 itself. That definitely is not allowed. We don't want the x plus 5 bracket to equal 0, so that means x can't be negative 5. And we don't want the x minus 2 bracket to equal 0, so x cannot equal positive 2 either. This next one is actually already a multiplication statement. So we're not going to have to do any inverting. We're not going to have to do any finding of reciprocals in this case. We are going to have to do a whole lot of factoring. And then hopefully we'll find lots of common factors that can reduce this further. So the first little expression we have on top, we can do some common factoring there. I'm going to factor out a 2. On the bottom, that's a trinomial. You can work with it for as long as you need, but eventually it's just like a simple trinomial, except it's got those extra y's attached, meaning that instead of just x's and numbers inside the brackets, we're going to have x's and y's. So it's x plus 5y would work, multiplied by x plus 2y. That would be a way to factor that. And then this is going to be multiplied by, well, again, a similar type of trinomial factoring on top, but this one would be x plus 5y and x minus 2y. So similar, except it's x minus 2y in that case. And on the bottom, that's actually a difference of squares. So x minus 2y and x plus 2y, oops, x plus 2y would be how that would factor. Now let's look for some reductions we can do. Well, I see I have an x plus 5y here, so I can divide the top by that to leave a 1 and divide the bottom by the same thing to leave another 1 as well. I see an x minus 2y, so I can divide by that on top as long as I find one on the bottom that I can divide by and leave a 1 as well once again. So what does that really leave me with? Okay, well, on top, I've just got the 2 times x plus 3y part left over, so I'll write those. And on the bottom, I have an x plus 2y and then another one of those exact same factors. So a slightly simpler way that I can write the bottom now is I just write x plus 2y squared, because I have 2 of those same identical factors. And now, can't forget in the end to state my restrictions. So what can x not be equal to? Well, again, in this case, it's not specific numbers, it's how they relate to y. So x cannot be equal to, for example, negative 5y. Because if it was exactly negative 5 times your y value, then that x plus 5y bracket would equal 0. For similar reasons, it also can't equal 2y or negative 2y. And we'll just do one more to show just how complex these can get, but to prove to you that no matter how complex they get, we can still handle it. So this last one here, it's a lot of division and it's a lot of factoring that we have to do. So let's start to work away at this here. So we have, first I'm going to just rewrite this as a product statement. So 2a squared plus a minus 15, 6a squared plus 3a, and now it's going to be multiplied by the reciprocal of the second piece, and also multiplied by the reciprocal of the third piece as well. Okay, so that's their step one is all done. Now we've written it as one single product, but now we have, as I said, a lot of factoring to do. So actually all 3 of the things we see on top are trinomials, and on the bottoms we have a combination of possibly some common factoring and maybe even difference of squares and trinomial factoring. So you can pause it now if you want and take your time and do all of that factoring on your own, or I'm just going to jump ahead and show you what my final factored form would be for all of this so that we can really just review that the reduction step one last time. So I got 2a minus 5 and a plus 3. On the bottom of that one, we can common factor out a 3a, which leaves 2a plus 1 on the bottom in another factor. 2a plus 1 and a minus 3 is how the top of that would factor. And on the bottom of this one, once again, we can do actually a little bit of common factoring first, and then it's a difference of squares factor, which becomes a minus 3 and a plus 3. And in this last one, trinomial factors on top break down into 3a plus 2 and a plus 1. And on the bottom, it's another trinomial factor with 3a plus 2 once again. That'll come in handy. And 2a minus 5. Okay, so that was a lot of factoring, and hopefully now you really believe those things that I was saying in earlier lessons when I warned you that factoring would be a very crucial skill. Well, you're already seeing later in this unit, but I promise you that we'll continue to use it in later units as well. So make sure you're comfortable with these factoring skills. Now let's reduce one final time. So where are some common factors that we can identify? Well, here's a 2a minus 5 that I can divide on top of this one, as long as I do the same way over here with this one. What else can I find? Well, I have an a plus 3 over here, so I'll divide by that on top, and I find an a plus 3 on the bottom. I can divide that as well. Let's keep using different colors. We have a 2a plus 1 here. I can divide that on top and divide the bottom by the same thing as well. I find another one there. And let's do blue this time. I have an a minus 3 on top here. Let's call that a 1. So we can make that a 1 by dividing by the bottom as well there. Running out of colors, let's try brown now. 3a plus 2 can leave a 1, and 3a plus 2 on the bottom will leave a 1 as well. So, all that being said, we do not have a whole lot left, but let's put it all together. So on the top, the only factor that we haven't used, or been able to reduce, I should say, is a plus 1. On the bottom, we had this extra factor of 3a and an extra factor of a. So really, it's like we have 3a squared on the bottom. Now, in terms of restrictions, this is where it gets really weird. Because with restrictions, we can't just focus on the denominators. What we need to do is focus on, first, the denominator of this original piece, but also we have to focus on anything that would make any of these expressions equal to 0. Now, why is that important? Why are we focused on the top and bottom of these? It's because both of those second two expressions, so in other words, this big rational expression and this rational expression, each of them are being divided. Well, remember, if anything makes anything in those rational expressions equal to 0, whether it's the top or the bottom, we won't be able to do division at all. So if something made their denominator equal to 0, then those rational expressions themselves wouldn't work. And if something made their numerator equal to 0, then we wouldn't be able to divide these things at all. So really, when we think about our factored form, we're looking for any values that make this equal to 0, or this equal to 0, or this equal to 0, or this, or this. We're looking for all of the things that could make any of those values equal to 0. If you take your time and think through it carefully, you'll end up with a pretty long list. You can pause it now and try and write out your own list. But here's the one that I got. A in this case could not equal -3, or -1, or -2/3, or -1/2, or 0 for that matter, or 5/2, or even +3. All of those are restrictions. If your a value happens to be any of those, then this rational expression as one overall expression simply cannot work. Because either a denominator somewhere along the way is going to be equal to 0, or you're going to be trying to divide by some other rational expression that is overall equal to 0. So all of those truly are restrictions to this final example. Once again, make sure you get some practice using the exercises attached to this lesson.